Okay, today we're going to talk about lines in three-dimensional space. Okay, now you remember that when you just have two dimensions, an x and a y axis, then you can write something like y equals mx plus b, where b is the y-intercept, right? And m is the slope. Well, that won't necessarily work here because, first of all, in three dimensions, a line doesn't even have to cross the y-axis, so there might not be any such thing as a y-intercept. Plus, the slope is a little bit more complicated as well. You can't just say rise over run because there's a third dimension. Okay, but here's what we are going to do. To explain a line, look in this picture. We have x, y, and z axis, and in blue I've drawn a line. In order to explain the points on that line, we need a point somewhere on the line, doesn't matter where, and a vector that describes the direction. Okay? And with those two things, we can completely describe every point on the blue line. Let's call that black point, let's call it capital P, okay? And let's say the coordinates are x0, y0, z0, or a lot of people say x0, y0, z0. Okay? Let's call that red vector, we'll call it D, because it's called the direction vector. Okay? Now every point on that line is reached by adding a multiple of D to the point P. Okay? However, let's be a little bit more careful here. How do you add a vector to a point? You can't do that, can you? So we need to do something a little bit different. We can't add a vector to a point, but we can add a vector to a vector. So I'm going to introduce a vector from the origin to the point P. Okay, and we'll call that vector P. Okay, point P is a point and vector P is a vector. That points from the origin to point P. So vector P would be the vector x0, y0, z0. Okay? All right, so let's look at points on the line. You see this point right here? That would be, whoops, let me make that smaller. That point is at what location? Well, let's make this a little bigger first of all. It's at the location P plus D, right? So vector P plus vector D would put you right here at that point. Okay? If I go to hang on a second, I didn't mean to erase all that stuff. Just want to erase that point there. Okay, that's fine. Let's put vector D back where it was. Okay, now if I go P plus 2D, then that would put me right here. Okay, it would put me at that location. I could draw a vector pointing from the origin to there. Okay, if I did, let's say, P minus 3D. Sorry, I'm trying to get rid of some stuff without getting rid of everything. Okay, if we did P minus 3D, where would that put us? That would put us like this. There's P minus 1D, P minus 2D, P minus 3D. That little one's off a little bit. Let me see if I can get that better. There we go. Okay. So that puts us right here. That last one right there was supposed to be red, but let's not worry about that. That puts us right here at P minus 3D. Okay, so the point I want you to get is this. Let's go way back now. The point I want you to get is that every point on that blue line can be described by the equation P, vector P, plus a multiple of vector D. Let's use T there as that variable. Okay, every point on that line can be described by that equation for some value of T. So if we would like to call that line L, then I can have an equation L of T equals vector P plus T times vector D. And that's a, by the way, that would give me a vector, right? So that's called the vector equation for the line. Okay?
I think it's because I answered the last one really quickly.
Okay, now this point right here is called the initial point of the line, but I want to make this really clear to you. That point could be any point on the line. It's not really the first point on the line. There's no such thing as the first point on the line. Okay, but some people call it the initial point. So let's summarize this. Okay, let's write this. If a line L goes through the point x naught, y naught, z naught, and follows the direction of vector D, and let's write for vector D, let's write ABC. Then the line can be described by the equation and then we write L of t equals P plus TD. Okay? And I'll put here next to that where P equals the vector x naught, y naught, z naught. Okay? And that's called the vector equation for the line. Okay, well, actually I'll change that. All right, vector equation for a line. Whoops. Okay. Okay, now let's take this a little further because there's other ways to write the equation as well. What if I just continued here? So we have P plus TD. Okay, let's put in what is P. P is the vector x naught, y naught, z naught. And then we have plus t times d, which is the vector ABC. Okay, so let's do that arithmetic. That would give us this. Plus this. Let's add those two vectors together. Okay, and here's our x coordinate. Here's our y coordinate. I should say component, x component, y component, and our z component. So that means I can write this. I can write x equals x naught plus at y equals y naught plus bt, z equals z naught plus ct. Okay, and those are called symmetric equations for a line. Sorry, I take that back. I'm using the wrong word. Those are called the parametric equations. Okay, so the same line could be written like this with one vector equation if you know an initial vector and the direction vector. Okay, or that same line can be written with these three parametric equations. Okay, or you can take it one step further and write it in one other way, which is this. Let's pick up from the parametric equations. Okay, I have x equals x naught plus at. Let's solve that for t. That would mean t equals x minus x naught over a, as long as a is not 0. From the equation for y, I can say t equals y minus y naught over b, as long as b is not 0. And from the equation for z, we can write t equals z minus z naught over c, as long as c isn't 0. So if a, b, and c are all non-zero, then t would equal all three of those, which means they would have to equal each other. And there we have what are called the symmetric equations for a line. But that's only allowable as long as a, b, and c are not 0. So there's three different ways that we can write equations of lines. We can write the equation of a line with a single vector equation, or three parametric equations, or three symmetric equations. Okay? That's how we represent lines in 3 dimensions. So let's just do a quick example. Okay, let's find the equation of this line that goes through the points 2, -1, 2, and 1, 3, -1. Okay, now there's lots of correct answers, so you might do it differently, but here's how I'm going to do it. Okay, what we're going to do is, let's decide on an initial vector. Okay, so for me, I'm going to choose the vector pointing to point P. From the origin. Okay, I'm going to use that as my initial vector. So that's the vector 2, -1, 2. Okay, we need to choose a direction vector. So that's any vector that points in the same direction as the line. Of course, a line goes 2 directions, right? So either one will work. So the easiest thing to do is to just draw a vector between the 2 points that we know. I'm going to go from P to Q. And there's our direction vector. Okay? So what is that vector right there? I want you to think about that. Okay, you got it? I'm going to write it down. That vector is -1, 4, -3. Why is it that vector? Because that's what you add to 2, -1, 2 in order to get 1, 3, -1. You see what I'm saying? If we add those three numbers to these three numbers, it will take us to these three numbers. Okay? Alright, so now we can write an equation for that line. The vector equation would be two, -1, 2 plus t times -1, 4, -3. There's the vector equation for that line. What would be the parametric equations? The parametric equations would be x equals 2 minus t, y equals -1 plus 4t, z equals 2 minus 3t. That would be the parametric equations for the line. What would be the symmetric equations for the line? The symmetric equations would be x minus 2 over -1 equals y minus -1 over 4. Of course, we can write y plus 1 over 4 equals z minus 2 over -3. So that's three different ways of describing that line. A vector equation, 3 parametric equations, or 3 symmetric equations. Okay, now let's answer this question. Does the point -1, 6, 6 lie on the line that goes through the point 2, 3, 1 in the direction of vector -1, 1, 2? Okay, so here's what we're going to do. We are first going to write down an equation for that line. So we'll write L of t, I'm going to write the vector equation, equals, okay, the line goes through the point 2, 3, 1. So I can write vector 2, 3, 1 plus t times our direction vector -1, 1, 2. Okay, that's the vector equation. What would be the parametric equations? That would be x equals 2 minus t, y equals 3 plus t, z equals 1 plus 2t. What would be the symmetric equations? The symmetric equations would be x minus 2 over -1 equals y minus 3 over 1, which equals z minus 1 over 2. Do you always have to write the vector equation, the parametric equations, and the symmetric equations? No, you don't, but I'm doing it for practice. Okay? Now, our question is this. Does this point lie on that line? Okay? I can answer that question using either one of those three. But for me, the easiest way to do it seems to be using the symmetric equations. because I have values for x, y, and z, which are -1, 6, and 6. Let's just plug those in and see if they fit the symmetric equations. So in other words, I'm asking the question, is it true that -1 minus 2 over -1 will equal 6 minus 3 over 1, and will that also equal 6 minus 1 over 2? It's a question. It's a yes or no question that we're asking. Well, let's see. This first one's a 3. The second one's a 3. And the last one's 2.5. Is it true that 3 equals 3 and 3 equals 2.5? No, it's not true. So the answer to the question is no. Okay, you see how that works? Okay, now next topic. When you only have 2 dimensions and you're given 2 equations of lines, there are 3 possibilities. Those 2 equations might be the same line, or they might be parallel to each other, or they might intersect each other. But when there's a 3rd dimension, there is a 4th possibility, which is the lines might pass by each other without intersecting, and those are called skew lines. Okay? I'm going to show you how to tell, if you have 2 lines, how to tell if they are the same, intersecting, parallel, or skew. Okay? So suppose we have line 1, and I'm going to write down here, we are given parametric equations for this line. Okay? We have x equals 1 plus 3t, y equals 2 minus t, and z equals t. For L2, we have the equations x equals -2 plus 4. I'm going to use the variable s this time. Okay? It's a different line, so I'm using a different variable. Y equals 3 plus s, and z equals 5 plus 2s. And I want to decide, are those 2 lines the same, intersecting, parallel, or skew? Okay, what I'm going to look at first is the direction vectors for these 2 lines. So L1, what's the direction vector for that? Let's call that vector D1. Do you see what it would be? It would be 3, -1, 1. Do you see that? Because it's made up of the coefficients of the t's. Okay, line 2 has this direction vector, 4, 1, 2. So the 2 lines have 2 different direction vectors, which means, well, actually, let me say something different. It's not just that they're different direction vectors. It's that those 2 direction vectors point in different directions. Okay, so since D1 and D2 are not parallel, then I can actually say two things. I can say line 1 is not the same as line 2. And I can also say that line 1 is not parallel to line 2. Now, just because D1 doesn't equal D2, that doesn't mean that it's not parallel lines, and doesn't mean it's not the same line. Okay, because remember, you can have different direction vectors for the same line. The question here is not, does D1 equal D2? The question is D1 and D2 in the same direction? Are they parallel to each other? Okay, and since they're not parallel, then these two lines are going in completely different directions of each other. So they're not the same line and they're not parallel. So the next question is, do these two lines ever cross each other? Okay, here's how we answer that question. The only way they could cross each other is if 1 plus 3t equaled negative 2 plus 4s, and at the same time 2 minus t equaled 3 plus s, and at the same time t equaled 5 plus 2s. The only way the two lines could cross each other is if those two green expressions were the same, the two yellow expressions were the same, and the two blue expressions were the same. So let's see if that's ever possible. Is it possible for 1 plus 3t to equal negative 2 plus 4s, and at the same time 2 minus t would equal 3 plus s, and at the same time t would equal 5 plus 2s? Is that ever possible? Okay, let's see. We're going to solve that system of equations. You learned how to do that in high school. You know how to do that. Let's take the third equation and plug it in to the second equation, the expression for t. So we would get 2 minus 5 plus 2s would have to equal 3 plus s. So that gives us negative 3 minus 2s would have to equal 3 plus s, which means negative 6 would equal 3s, which means s would be negative 2. Okay. And since t is 5 plus 2s, that means that t would have to equal 5 minus 4, which would equal 1. Okay, so in order for those two to be equal to each other and these two to be equal to each other, the only way that's possible is if s is negative 2 and t is negative 1. Well, if that's the case, then would 1 plus 3t be equal to negative 2 plus 4s? Let's see. That would be 1 plus 3t. Is that equal to negative 2 plus 4s? That's a yes or no question. So this would be 4. Is 4 equal to negative 10? And the answer is no. So you see, in order for a point to lie on both lines, well, it would be impossible. because if they have the same y value and the same z value, they cannot have the same x value. So that means the lines don't intersect. So they're not the same line, they're not parallel, and they don't intersect. So then we can conclude that they must be skew. Okay? That's how you answer that question. If they did intersect, then how would you find the point where they're intersecting? All you would do is take your value for s and just plug it into these three equations. Or take your value for t, or take your value for t and plug it into these three equations. Either one, you would get three coordinates, x, y, and z, and that's the point where the two lines cross each other. Okay, next topic now. Okay, what I want to do next is show you this. Suppose you have a line and you have some point. Let's call this point Q. And you want to find out the distance from Q to the line L. Okay? Now, how do you measure the distance from a point to a line? Well, I think we can agree that when we say the distance, we mean the shortest possible distance. So, not that distance, not that distance, but that distance. In other words, we want to draw a segment that goes from Q down to line L and is perpendicular to line L. That'll give us the shortest distance. Okay? I'm going to call that H. Okay, and we want to find that distance. Well, it's pretty easy to do. You have to remember something. When we are given line L, okay, we can find an initial point and a direction vector, right? Now, I don't know where that point will be. Just for the sake of argument, let's draw it over here. Okay, we're either given an initial point or we're given the equation of the line L, and once we see the equation of the line, we can pick out the numbers from the equation to tell us the initial point. Okay, we can also pick out the numbers from the equation to tell us a direction vector. Okay, here's what we're going to do. Let's draw in the vector from P to Q. Okay, we'll call that vector PQ right like this. There's an angle here. I don't know what it is. Let's call it theta. Now, I know a couple of things. I know from trigonometry that the length of h equals the length of vector PQ. I'm not putting magnitude symbols around h because h isn't a vector. Do you see that? There's no arrows on that line segment. Okay, times the sine of angle theta. That's just from trigonometry. Sine equals opposite over hypotenuse. Okay. Oh, be careful here. H doesn't stand for hypotenuse, does it? Okay. The hypotenuse is vector PQ. Okay. So H equals the magnitude of PQ times sine of theta. Okay, but we also know something else from our previous lectures. We also know that the magnitude of the cross product vector PQ crossed with D equals, do you remember what that would equal? It would be the magnitude of PQ times the magnitude of D times sine of theta. Okay, which equals, let's write it this way, magnitude of D times magnitude of PQ sine theta. So that's the magnitude of D times H. So that means that H equals the magnitude of PQ cross D divided by the magnitude of D. That's how you find the distance from a point to a line. So what is it you have to do? You have to look at the equation of the line to find the direction vector D and to find a point P. You take that point P and your point Q in order to get the vector from P to Q. And then that's all you need is the vector D and the vector from P to Q. Okay, and then you can find the distance between two lines. So why don't we practice that real quick? How far is the point let's see, 1, 1, 1 from the line two, 1, 3 plus t times 2, 1, negative 2. Okay? All right, let's answer that. Our direction vector is 2, 1, negative 2. Okay? And our vector PQ what do you think that is? So let's think about this for a second, okay? Q is the point 1, 1, 1. P is the point what? 2, 1, 3. So the vector PQ is the vector from 2, 1, 3 to 1, 1, 1. In other words, what do you add to 2, 1, 3 in order to end up at 1, 1, 1? The answer is negative 1, 0, negative 2. Okay? And now we just follow our formula that I have highlighted up there. Okay? So we'll calculate PQ cross D. Let's do that. So now make sure you do it correctly. I'll go ahead and give you some time to work it out. Pause the video if you need to, because I'm about to write down the answer. It's negative 2 to negative 1. Okay? So that's PQ cross D. What's the magnitude of PQ cross D? That's the square root of negative 2 squared plus 2 squared plus negative 1 squared. So that would be 4 plus 4 plus 1, which would be 9. That's 3. What's the magnitude of D? That's the square root of 2 squared plus 1 squared plus negative 2 squared, which is also 3. So the distance from our point Q to our line L is 3 over 3, which is 1. It's 1 unit away from the line. Okay? All right, last topic for this video. How do you find the distance between two lines? Suppose we have two lines. Let's call that one line 1. And then we have line 2. Now, right now it looks like those two lines are going to cross each other, but not necessarily, because this is in 3 dimensions. So line 2 might be going from front to back, you know, might be pointing into the page, for instance, and line 1 might be laying right flat on the page. Okay, so these might be skew. For that matter, they might even be parallel, and I just didn't draw the picture very well. Okay, the point is, you can't just rely on the picture. I know we say that in math all the time, but especially when you're doing 3-dimensional stuff and your picture is only 2-dimensional, you can't trust the picture at all. Okay? Now, what I do know is that there would be an equation for the two lines, and from the equations I can pick out initial points. So let's call that P1 and let's call this P2. And I could also pick out direction vectors. We'll call this one vector D1, and we'll call this one vector D2. Okay, now if I want to find the equation, the distance between those two, what I need to do is, I can't tell where it is in the picture, but somewhere these lines reach their closest distance from each other. That's where we want to measure the distance. Okay? And what I can say about that is it will be parallel, perpendicular to both of those lines. That's where the distance gets measured. Okay, so there's something we need to do. We need to find a vector that points in the direction of that black line segment that I just drew. Okay, now, so what I'm trying to say is this. Let me do this for you. We need to find a vector like that points along the direction of that black line segment. Okay, let's call that C. Then C would have to be perpendicular to D1 and also perpendicular to D2. Okay, how can I find a vector that's perpendicular to D1 and D2? Well, if you think about it, isn't the cross product of two vectors orthogonal to both vectors? So therefore, I can choose C to be the vector D1 cross D2. See, I didn't have C before. We were like this. We were in that situation right there. I calculate D1 cross D2, and that gives me a vector, and I call that vector C. Okay, now I know that C will be perpendicular to both D1 and D2. So C will either go this direction or this direction. It doesn't matter which one. Okay, so I'll draw it like this. But if it pointed the other direction, exactly opposite, that would be fine as well. That doesn't matter. The only thing that's important is that it's orthogonal to both of the direction vectors. Okay? And now, this part is not obvious. Okay? So this part here I'm going to ask you to kind of trust me on, and that is, how do we find vector H? What we do is we take the vector from P1 to P2, whoops, okay, and then we find the projection of that vector onto this vector, and whatever the length of that projection is, that's what H will be. Okay, so in other words, H equals the magnitude of the projection of the vector from P1 to P2 onto the vector C. So you have to go back several lectures if you need to remember how to do that. Okay, that's going to be projection equals, I just want to remind you, that projection is this. The vector from P1 to P2 dot vector C divided by the magnitude of C times vector C. Now we want to find the magnitude of that. So that's going to be the absolute value of the vector from P1 to P2 dot vector C divided by the magnitude of C times, oh, by the way, I'm sorry, that was supposed to be squared. I'm sorry, I left that off. That's part of the definition of projection, is that the magnitude on the bottom is squared. Okay. And then times the magnitude of C. Do a little bit of canceling. And what are we left with? The absolute value of the vector from P1 to P2 dot vector C divided by the magnitude of vector C. That's how far apart the two lines are. Okay, so let's practice one of those. How far apart are, and then I'm going to write down two lines here. Line number 1 that's going to be 1, 2, 1 plus t times 2, negative 1, 1. And then line 2, that's going to be 3, 3, 3 plus t times 4, 2, negative 2. Okay? How far apart are those two lines? So, what can I say here? P1 is the point 1, 2, 1, and direction vector 1 is the vector 2, negative 1, 1. P2 is the point 3, 3, 3 with direction vector D2 4, 2, negative 2. Now I want to point out something that is not important for this question, but I just want to point it out to you. Well, actually, no, I'm not going to point it out, because what I was about to say I realize is not quite correct. It looked to me like D1 and D2 were parallel to each other, but now I see that they're not. I thought that D2 was just twice of D1, but now I see that the signs don't agree. Okay, so let's find how far apart those two lines come from each other. Okay, so we need to find vector C, which is the cross product of D1 and D2. You could also do D2 cross D1, and that would still work. Give you a different vector, but it'd still work. Okay, so let's find that. So I'm getting 0, 0, Let me double check that really quick. Those first two, I'm going to do them again, make sure I got them right. 2 minus 2 is 0. Okay. Ah, yes, that middle one's not a 0. Good thing I'm checking. That should be 4 minus negative 4, so that's actually an 8. Okay, good. And then we have 4 minus negative 4, which is 8. Okay, so there's the cross product of d1 and d2. Okay, let's find the vector from p1 to p2. Okay, what do you add to p1 to get p2? That should be 2, 1, 2. So let's calculate the dot product of the vector from p1 to p2 dot with the vector c. So that's going to be the square root of, sorry, there's no square root with dot product, is there? I was thinking magnitude. Okay, so the dot product is going to be 0 times 2. Let's write 2 times 0 will make more sense. Plus 1 times 8 plus 2 times 8. And what's that equal? 24. What's the magnitude of vector c? That's the square root of 0 squared plus 8 squared plus 8 squared. Which is 8 root 2. So the distance between those two lines is the absolute value of 24 divided by 8 root 2. So that's 24 over 8 root 2. Whoops, not 3, 2. So that's 3 over root 2. Okay? Or if you don't like square roots in your denominator, that would be also the same thing as 3 root 2 over 2, if you prefer that. That's the distance between the two lines at their closest point. If the lines actually were intersecting each other, then that distance would have come out to be 0. Okay, that's all for this lecture. Have a good day.